The hypothesis of a massive ancient explosion is widely accepted by scientists as the primary explanation for the origins of the universe, encompassing the creation of stars, planets, and all life, including humanity. Despite its somewhat peculiar name, the term Big Bang effectively conveys the enormity of the event. Initially, the universe consisted of a dense collection of particles squeezed into a space smaller than a pinhead. From this point, a colossal explosion of matter occurred, known as the Big Bang, succinctly summarizing the process that unfolded over billions of years. However, despite the continued support for the Big Bang theory, advancements in scientific knowledge have consistently challenged its predictions. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory to date, researchers anticipated that its observations would strengthen the Big Bang theory. Unfortunately, after just 1 year in space, the telescope has astounded scientists with its groundbreaking capabilities, offering extraordinary glimpses into the universe's past. The JWST's findings have revealed systems so ancient that they could potentially reshape our understanding of the universe's origins, sparking immense interest among scientists and enthusiasts alike. One such significant discovery came when astronomer Rohan Natu, analyzing early images from the JWST, unexpectedly found a galaxy that surprised everyone. This galaxy, named Glass Z13, appeared to be unusually massive and dated back to only a brief time after the Big Bang, making it older than any previously observed galaxy. Natu shared this discovery with colleagues on Earth, describing it as something beyond what astronomers had ever imagined. The JWST, located far from sources of interference and equipped with cutting-edge technology, was designed to probe the earliest era of the universe, known as the Cosmic Dawn. This period marks the formation of the universe's first stars and galaxies. By examining galaxies from this era, scientists hope to refine their understanding of fundamental cosmic processes, such as the influence of dark matter and dark energy. Expectations for the JWST's findings were modest, with researchers predicting the discovery of galaxies located billions of years away. However, the telescope's observations exceeded all projections. The images it captured revealed galaxies in advanced stages of development, challenging existing models and sparking intense debate. As scientists continue to analyze the JWST's data, the implications of these discoveries could be monumental, ushering in a new era of cosmological research. These astonishing revelations from the JWST offer a tantalizing glimpse into the universe's past, propelling humanity's quest to uncover the secrets of existence. As early galaxies began to appear, researchers and astronomers scrambled to comprehend them. Could these unusually large and bright early galaxies be an anomaly, perhaps caused by flaws in the telescope's initial observations? Or, if they are accurate, could they somehow fit within the established cosmological models, or do they suggest that the universe is more complex and strange than previously imagined? The question remains: how should we interpret the emergence of our known universe from the chaotic early stages? The JWST's early discoveries may force a re-evaluation of our understanding of cosmic history, shifting our focus not only to distant epochs in faraway galaxies but also to our own existence here in the present. As Mark McCarran, a senior scientist at the European Space Agency, associated with JWST, remarked, "You build these machines not to confirm the model, but to break it. You just don't know how it will break." In many ways, the JWST's observations of early galaxies are the culmination of decades of effort. The groundwork for this telescope began in 1985, when the Hubble Space Telescope was still operational but nearing the end of its life. At the time, ESA's director Ricardo Jan advocated for a follow-up project, despite initial disagreements about focusing on Hubble. His vision led to the development of what would later become the JWST, an advanced instrument designed to observe the universe in infrared light, allowing it to peer deeper into space than Hubble ever could. The necessity of the JWST became especially clear in December 1995, when astronomers used the Hubble Space Telescope to capture the Hubble Deep Field image. Despite doubts about discovering anything substantial, the resulting image revealed thousands of galaxies stretching back more than 12 billion years. This discovery demonstrated the need for a more advanced tool, and after 2 decades of development, The JWST was finally launched on Christmas Day 2021. After passing a rigorous series of tests, the telescope reached its destination in space a month later, ready to begin its mission. By July 2022, the JWST was poised to begin its first year of science observations. Part of this mission focused on high-impact programs, including the cosmic evolution and early universe surveys. Astronomers dedicated extensive time to studying various regions of the sky, seeking to uncover early cosmic structures. Initially, scientists expected modest findings, similar to a more detailed version of the Hubble Deep Field. But what they discovered was far more surprising. Stephen F. Lynn, a leader of the SE project from the University of Texas at Austin, initially believed that galaxies from such distant periods would require multiple data cycles to detect. To their astonishment, these galaxies appeared much earlier than anticipated. The record for the most distant known galaxy was previously held by GNZ11, observed in 2015 with a redshift of 11, indicating it was among the furthest galaxies from us. However, the JWST discovered galaxies with a redshift of 13, pushing the boundary even further, showing that they existed shortly after the Big Bang. These findings were further confirmed by two independent teams, including one led by Rohan Natu, who identified glass Z13 with a redshift of 13, confirming its immense distance and mass. The rapid emergence of such massive galaxies challenges the predictions of the standard cosmological model, known as lambda cold dark matter, lambda CDM. To understand this phenomenon, it is crucial to revisit the early stages of the universe. The JWST's observations have illuminated an unprecedented era, revealing galaxies that are unexpectedly bright and massive for their age. Some of these galaxies exhibit masses as large as 1 billion suns, comparable to our own Milky Way. The implications of these findings are profound and could lead to a significant shift in our understanding of the universe's early evolution, as well as the nature of cosmic growth during the first few 100 million years after the Big Bang. After the tremendous explosion, the universe was a hot, dense soup of fundamental particles. As the universe expanded and cooled, helium and other light elements formed, leading to the creation of the first atoms around 400,000 years after the Big Bang. About 100 million years later, conditions became favorable for the formation of the first stars, primarily composed of hydrogen and helium. These early stars were much larger and more spectacular than those we see today, and they began to form into protogalaxies, drawn together by the gravitational pull of dark matter. However, the James Webb Space Telescope, JWST, has challenged this model by revealing massive, distant galaxies much earlier than expected. Stacy M. from Case Western Reserve University noticed a surprising absence of smaller protogalactic fragments, suggesting that some galaxies may be closer than previously thought, hidden by dust and appearing dimmer. The discovery of these early galaxies raises important questions about the early stages of the universe and highlights the need for continued research and updates to our cosmological models. A follow-up observation of the galaxy GNZ13 in August 2022 by the Atacama Large Millimeter Array ALMA in Chile cast doubt on the initial findings. Despite using advanced brightness-based measurements, ALMA failed to detect key emissions associated with GNZ13. As P. Tom B. from Goya University, who led the observations, explained, this suggests that lower redshift interlopers may be present but that ALMA couldn't detect them. This situation underscores the challenges of confirming JWST's groundbreaking discoveries. Rohan Natu, one of the experts involved in the research, expressed the uncertainty surrounding these findings. He mentioned that while the good news is that there's still no concrete evidence to dispute them, the bad news is that JWST might not be able to independently verify its own results. The most concerning implication could be that the standard lambda CDM cosmological model may need a significant revision. Michael Bohan Cullen, a cosmologist, emphasized how unexpected these results are, indicating that they are difficult to explain within our current cosmological framework. This has led to theories such as modified Newtonian dynamics, MOND, which challenge the existence of dark matter. JWST's findings might lend support to these theories, but not all cosmologists are convinced of MOND's validity. Another explanation is that early galaxies might have formed with little to no dust, making them appear more luminous and skewing mass estimates. This could also explain why ALMA struggled to detect GNZ13. Charlotte Brickley and her colleagues proposed that JWST might be observing some of the most massive, energetic galaxies from the early universe, suggesting that conditions for star formation in this era could have been more favorable due to higher gas pressures and temperatures, possibly influenced by early magnetic fields. The rapid dissemination of scientific papers based on JWST's early findings reflects a shift toward faster, collaborative research, often using platforms like A14 in virtual space. While this accelerates the spread of discoveries, there are concerns that rushing to conclusions may overlook critical details and recalibrations. Despite this, the sheer number of high redshift galaxies discovered by JWST indicates that the early universe might be very different from what was once believed. Fin Lin expressed confidence in the validity of the findings, suggesting that the chances of cosmologists being completely wrong are minimal. Currently, astronomers are working to coordinate follow-up observations with JWST. Nancy Levinson is reviewing around 12 proposals from different teams, seeking additional JWST observing time to explore high redshift galaxy candidates. Given the significance of these early discoveries, confirming them is crucial. Troy, who submitted one of the proposals, highlighted the importance of verifying these revelations. Other initiatives like the Universe Web project led by K2T aim to broaden the search for early galaxies by observing larger areas of the sky for extended periods. They hope to uncover a wealth of new information and identify possible signs of the first proto-galaxies, potentially looking for evidence of early stellar deaths and stellar explosions as markers of these ancient structures. Some theories suggest that JWST could detect galaxies at a redshift of up to 26, just 120 million years after the Big Bang. Even discovering a small group of such galaxies would be a remarkable achievement. As Nata pointed out, astronomers are not discouraged by the uncertainties and are excited about the new era of science that JWST has ushered in. Despite challenges, the rapid sharing of new data has reinvigorated the scientific community, fostering a sense of camaraderie and collaboration. In summary, the James Webb Space Telescope has ushered in a new age of exploration, pushing the boundaries of our understanding of the universe's origins and evolution. Its groundbreaking observations of galaxies formed shortly after the Big Bang have sparked both excitement and debate among researchers, challenging traditional models and prompting the development of new theories. From the mysteries of dark matter to the secrets of early star formation, JWST's discoveries hold profound implications for our understanding of cosmic history. Looking ahead, JWST promises to continue unraveling the universe's complexities, offering glimpses into phenomena that were once beyond our reach. Its findings not only advance scientific knowledge but also inspire awe and curiosity about the vastness of the cosmos and our place within it. As JWST continues its mission, astronomers eagerly anticipate the next wave of discoveries, inching closer to answering the fundamental questions of existence and deepening our fascination with the universe's grand narrative.